So we've spent a lot of time talking about the wave model of light, and I mentioned at the start of this unit there were two kind of really big models that fought one another. We had that wave model of light, which we really explored in depth, but I also mentioned we had this particle model that Newton kind of proposed early on. Now we've studied the wave model in a good bit of depth, and we've certainly established that light certainly does behave like a wave, but we actually have to go back to the particle model because there is evidence that supports light behaving like a particle. This is what we're going to explore now for a little bit. The big things we're going to look at are the photoelectric effect and Compton effect, but there's a few other little things that we're going to sprinkle in here. So let's get started on this. Now, by the time we finished up and got to the 20th century, so by the time we got to the 1900s, pretty much everyone, the prominent scientists, figured that all of physics was done. We solved every problem. There was nothing left for us. Now, there was kind of two big problems that came up. So the first thing is physicists didn't really know how to explain the relationship between temperature of an object and the color of light it happens to emit. This problem is the basis of quantum mechanics, and this is what we're going to actually scratch the surface of, and I mean the literal surface of. The other big thing that physicists didn't really know how to interpret was this Michelson-Morley experiment. So, without going into too much depth, they wanted to prove the existence of this thing called the luminiferous ether. When we talked in Physics 20 about waves, we talked about how mechanical waves need a medium to propagate. Like something has to cause it. It has to have some medium for it to actually travel through. Like, for example, a sound wave needs air, a water wave needs water. But we said EM waves don't actually need a medium. Well, the theory back in the day was the medium that EM waves travel in is this thing called the luminiferous ether. So Michelson and Morley went out to prove it. They actually ended up disproving its existence. That's the basis of special relativity. We won't be looking at that. So these two kind of big problems that came up at the start of the 1900s or the end of the 19th century, this is basically what we would call the starting point of modern physics. So what we're doing is we're transitioning from the classical era, which is based a lot on the works of Sir Isaac Newton, and we're starting to go into the modern era where we're going to look at people like Max Planck, Albert Einstein, and many others. So the first thing we want to look at is we want to look at this thing called blackbody radiation. And this has to relate to the old idea that there is a relationship between color and temperature. And you already know this. If you were a young kid and you saw the element on a stove glowing red, you probably knew that was hot, or you learned the hard way that it was hot. So you knew that red meant hot. So you could establish that link. So we have some graphs here that are showing intensity as a function of frequency. And you're noticing that we have different temperatures, and we're noticing that they peak at different frequencies. So again, this is showing that there has to be some link between temperature and color, because frequency dictates the color or the part of the spectrum that we're in. It doesn't necessarily have to be visible light. So from these graphs, there's a few things that we can interpret. First of all, hot glowing objects, they emit what we call a continuous range of wavelengths, and hence a continuous range of color. What this means is that it's emitting all wavelengths of color, and it may emit different forms of EMR, like UV or infrared. Now, for a specific temperature, we're going to find that the light emitted has a characteristic wavelength, which essentially determines the color of the object when it glows. So if I kind of go back for a second, we see these graphs here. We see that for different temperatures, they kind of have a different peak at a different frequency. So this is corresponding to that characteristic wavelength or characteristic frequency for that temperature. And then the hotter the object happens to be, the bluer the light it's going to emit. The cooler, the redder the light's going to emit. And some of you who took chemistry know this when you're dealing with Bunsen burners. We're talking about the hottest part of the flame being the blue part. So those graphs we looked at, those are referred to as black body radiation curves, or BBR curves. And they basically show the intensity of light as a function of frequency or function of wavelength for an object specifically at a fixed temperature. So we're looking at one particular temperature. Now, we've mentioned this word black body, so what do we mean by a black body? Basically, for us in physics, a black body is something that's going to absorb all energy that falls upon it. Now, you might think, well, how do we get black? Well, if something absorbs all the energy on it, none of that energy is coming back to our eyes. So in that absence of energy, we're going to interpret that as black. Now, what was also noted is that objects that are perfect absorbers of heat, they're also perfect radiators of heat. And then this energy that gets radiated out from this black body, this is what we can look at on the black body curve, which as we saw is really only dependent on temperature. So as we change the temperature, that is going to shift the peaks. Now, why have we talked about this? Like, what's kind of the point to all this? Well, this leads into something called the ultraviolet catastrophe. And this is where we start to have that tension between kind of Newtonian physics and sort of the modern world. So this establishment of the link between color or wavelength frequency and temperature, it was first established by two gentlemen named Raleigh and Jeans. So what they developed was something called the Raleigh Jeans Law. Now, Raleigh Jeans, their law, their experimental evidence and their theoretical predictions agreed for large wavelengths or low frequency. But what happened is when they went to shorter wavelengths or higher frequencies, they had a little bit of a discrepancy. So we can kind of see here in the graph, we can see these different black body curves we have for 3000 Kelvin, 4000 Kelvin, 5000 Kelvin. So these are the experimental evidence. This is the experimental curves or the modern theoretical curves. Now, Raleigh Jeans' curve, up at these higher wavelengths, we have a good agreement between the curves. But then as we start to move closer and closer to the UV spectrum, we notice that the energy starts to kind of skyrocket up. And what Raleigh Jeans basically figured out is by the time we get to the UV spectrum, we're starting to have an infinite amount of energy in our radiation that's emitted. Now, if that sounds a little bit crazy, it absolutely is. What that's saying is, if I lit a match, matches will emit colored light. Like we can see the flame. It's also going to emit infrared radiation. It's also going to emit a little bit of UV. So what Raleigh Jeans predicted is if I lit a match, because it's emitting UV radiation, well, UV radiation has essentially an infinite amount of energy. So by lighting a match, I should be able to basically explode the entire world, the universe, and get rid of it. We know now that doesn't happen. You light a match, it's going to burn, and that's that. So no destruction of the universe. So Raleigh Jeans had a really, really big flaw. It worked well for high wavelengths, not so much for low wavelengths, and they had to figure out what the problem was. So this whole issue of infinite energy in the UV spectrum, this is what got referred to as the ultraviolet catastrophe. So this was a huge conundrum in the early part of modern physics. Now, like we said, here's our Raleigh Jeans law. So this is kind of the classical prediction. So as we go up towards the UV spectrum or go up to UV frequencies, energy is going up towards infinity. What we now know in the quantum or sort of we'll call it the modern physics approach, we kind of have the energy increasing. We're noticing it peaks, and then it's going to kind of decrease. So this curve here, this accurate or more modern one, this is referred to as a Planck's law curve. It was proposed by a German physicist named Max Planck. We'll talk about him in a second. You'll see the equation here for Planck's law. Do not worry about that. You will not need to know this equation for high school. So we're going to talk about Planck, but his curve here, when Planck proposed this, it answered one question, but then it brought up more questions. So first off, it asks, well, why did the frequency happen to drop off at a particular point? So in this case, why did it kind of drop in the UV region? And then the other thing is, why does the Blackbody radiation curve peak at particular frequencies for different colors? So those were kind of the two welcoming questions to modern physics. And like I said, we're going to scratch the surface of these questions. We're not going to go into a lot of depth. To do that, you'll have to take a quantum mechanics course at the university level.